So good evening, everyone. My name is Jyoti Sharma, and this session will be from 7 to 9. Can you please confirm whether I'm audible to you or not?
Yes,
Yes,
ma'am.
ma'am.
Audible.
Okay, thank you so much. So, what we will cover today, this is lecture 31 to 35, and mostly we will cover this secondary treatment because in last week, we were trying to discuss about this primary treatment, and in secondary treatment, we have activated sludge process unit. We will discuss something about our trickling filter, then anaerobic sludge blanket reactor, then lagoons, a little bit about the sequential batch reactor and granular activated sludge process. Then we have some slide on phytoremediation and phycoremediation. So this will be our content for today. So I want to recall something that we started with the primary treatment, right? So we started with the primary treatment. We had polluted water that has been emitted either from industries, or let's say agriculture, or even from households. So in case we do have polluted water and we need to clear that water, then we do have four steps to clear the water. The first is primary treatment, then secondary treatment, then we have tertiary, and within tertiary we may have disinfectant and another advanced processes that we can have. And before this primary treatment we may have pre treatment, right? So that's how we do have four step, and we have to go one by one. And in primary treatment, in last week, we discussed how we can use different screen, then grid chamber, then how we can break different kind of plastic and everything into smaller part, and sedimentation, filtration. We talked about this, right? Then this week is just about this technical part of your secondary treatment, and we already have discussed secondary part involves microorganism. So with the help of microorganism we treat the water. Or mostly focus will be on this secondary treatment and little bit about disinfectant if time allows to us. So this is a brief what we will discuss today. um, this is just I want to show you that in primary treatment we already have discussed bar rack and bar screen, grid chamber, equalization tank, and sedimentation tank. Different type of settling we already have discussed, and something technical and engineering part of how we can build bar, chamber, equalization tank, what is the principle, then what should be the length and breadth of this. So we already have covered a little bit about this primary treatment equipments. So move on to secondary treatment, and this is again the previous week slide, in which I told that in secondary treatment we have some conventional treatment option and some are advanced treatment option. If we are having lagoons, so lagoons are just like shallow lakes or pond that we have. Using that shallow lake or pond we can treat the water, so this will come under lagoons. Aerobic digestion with the help of like whenever we have organism and we are giving oxygen, then this will come under the aerobic digestion. Activated sludge process, this is the part of aerobic digestion. Then anaerobic in the absence of oxygen, but again we are using microorganism to clean the water. Then UASB, this is again anaerobic digestion. We will talk about this as well. Then biofilter. So this will come under conventional treatment option. But if we are talking about this advanced, then this will be granular activated sludge process, sequential batch reactor, membrane bioreactor, phycoremediation and phytoremediation, bioelectrochemical system. So in conventional, today we will talk about at length about this activated sludge, anaerobic digestion, UASB. And in advanced treatment we will talk about phycoremediation and phytoremediation. So this will be the topic that we will cover today. And if you have any problem anywhere, you can interrupt me, you can write in the chat box, and I encourage you to speak, communicate, write in the chat box, so that the learning can be happen in both ways, right? So I'm starting with this slide, that different processes that I talked about, these secondary processes, so in which a microorganism may have attached to some surface, or microorganism may be suspended in the liquid. If it is suspended in the liquid, then this will come under the suspended growth, and if it attached to some surface, then it will come under attached growth. And there are some example in suspended growth, what kind of processes will be considered, and under attached, what kind of processes will be considered. We also have categorized our processes in aerobic process or anaerobic, so whether there is a presence of oxygen or not, so this is how we can classify. Okay, so this is the brief discussion about your secondary treatment. Now I will have a lot of MCQs. Based on that, we will learn more. Okay, so the first part is activated sludge process, and let me give you a little introduction about this. So this is something like this. We have some polluted water, right? Polluted water is coming from, let's say, some pipe. We have aeration tank. In that aeration tank, we have already liquid plus microorganism. We already have liquid plus microorganism, and when this wastewater will come into this, then this microorganism, because wastewater will have some organic matter, and these organic matter will be degraded by this microorganism and will be converted into CO2 and H2O, and that will be released. So after that, purified water will be transferred to another chamber, and this is the final settling tank, where some of the waste will have microorganism or sludge, that will be settled down, and then your pure water, not pure water, but a little bit clean water, maybe for move forward. Okay, so this is activated sludge. So here what we are doing, microorganism is present in some liquid, and then wastewater will come into that aeration tank. There will be a degradation of organic matter in the presence of oxygen, and then a little bit clean water will move further for the next step. So this is all about activated sludge process. And okay, uh, the advantage of your activated sludge is that it can remove your BOD by 85 to 90%, even if it is the conventional way of processing. Then this we will talk about this later. Right now I'm not talking about this, because I want to start first with MCQs. Okay, so because little bit we will talk about technical terms today in activated sludge process or even in trickling filter, so you have to respond me. Okay, so the question is, in the activated sludge process, which parameter represent the balance between food availability and microbial population? And four option I have are MLSS, F by M ratio, MLVSS, BOD utilized. Okay, so let me see the answer that you have given to me. So Divya and Venkatesha gave me B, that is the food and microorganism ratio. So yes, B is the right option. that the parameter that balance food availability. So food availability means, whenever you have polluted water itself have some organic matter, and microorganism need that organic matter to for the growth. Okay, so food availability will come from your wastewater, because wastewater will have organic matter. And population grow microbial population growth will be dependent on how much food they have. Okay, so this can be balanced by F and M ratio, and this is very important for us. uh, okay, let me show you first. Okay, you have to understand the formula for F and M, and this is Q S node Vx. F and M, you know that this is food, this is microorganism. Q is your influent flow rate. So the flow rate with which your wastewater is coming in the aeration tank. So this is your Q. S is your substrate concentration. So how much BOD? So this water is coming, right? That water is the wastewater. So how much BOD that we have in that wastewater? BOD means how much biological oxygen demand that we need, because organic compound, let's say it is H6, sorry, say 6 H12 or 6, then to degrade this we need oxygen, and that will convert this, let's say, CO2 and H2O. So how much oxygen is needed to degrade this will be the BOD. So whenever we have higher load of organic compound, then that means BOD will be increasing, oxygen demand will be increasing by the microorganism to degrade that organic matter into very simpler substances. Okay, so this is your substrate concentration, or it can be usually in BOD or COD. Then volume of your aeration tank, this is your aeration tank. And then X is your concentration of microorganism. So how much microorganism we have in this aeration tank? So just remember, F upon M is equal to Q S node upon Vx. So can you tell me, okay, we have F and M ratio, right? What will happen if it will be higher, or what will happen if it will be lower, uh, in the form of BOD removal? So BOD will be removed, so the efficiency to remove the BOD will be higher in what case? When BOD, F and M ratio will be higher or lower? Can you tell me something about this? Because ultimately in secondary treatment we want to remove this BOD, we want to remove the organic matter, and we should have very sufficient F and M ratio. Can you tell me it should be lower or higher to increase the efficiency of BOD removal? Can you write in chat box, or can you speak a little bit about this? This F and M ratio should be higher or lower to increase the BOD removal efficiency. Okay, I tell you, don't worry about this. Um, Not higher. That's why I asked the question. This is not directly proportional. This is inversely proportional. Let me tell you how. Okay, so I don't have right now this, but okay, let me tell you. uh, we have food, right? And we have microorganism. Whenever we will have more food, more food means the microbial age. So microbes are prokaryotes, right? These are not the eukaryotes. So microbes are mostly bacterias. So let's say this is the one bacteria. Okay, and one bacteria, if it will have sufficient food, so if food is more, then this bacteria will replicate and will form into two. Okay, so it will replicate and it will divide into two. Okay, so it means the age of this bacteria is now lower. Okay, so more of the sludge we will have. And if we do have like less food, then what will happen, this reproduction or this dividing into two will be less, and that's how this will be one bacteria, and that one bacteria age will be longer. And whenever this age will be longer, the BOD removal efficiency will be higher, and sludge will be less. Okay, so that's how this is something inversely proportional. Okay, so we have fraction of MLSS actively involved in consuming the incoming substrate is. So first we have MLSS, that is mixed liquor suspended solid, and the fraction of it that involved in consuming the incoming substrate is. It is already MLSS, then I don't think that A will be same. Okay, so can I say that B is the right option? Okay, so Priscilla gave me B option, but okay, don't worry about this. I just try to explain you. So firstly, the B is the right option, but you have to understand what do you mean by this MLSS. So MLSS is nothing in the aeration tank. So we have aeration tank in which wastewater will come in, and then little purified water will go out. So in this aeration tank we have microorganism. Okay, and we have liquid. So liquid part is known as liquor, and these microorganisms are known as your suspended solids. Okay, in this terminology, and because these are mixed, then this aeration tank, it means liquid, that is water, water plus microorganism will be known as mixed liquor suspended solid. Okay, but some of the portion that will consume the incoming substrate means polluted water have organic matter, and this organic matter will be the substrate or food for your microorganisms. So the portion of MLSS that will involve in consuming the incoming substrate will be known as mixed liquor volatile suspended solid. Okay, so B will be the right option. And why C is not the right option? Sludge recycling solids are are the microorganism that we have to recycle to put again into the aeration tank after sludge formation. So this is not exactly the portion that would involve. It may or may not involve to consume the incoming substrate. That sludge recycling solid first will be the part of MLSS, and then it may or may not be MLVSS. So that's how B is the right option. So let me show you. So just see here, the combination of liquid and microorganism in aeration tank is called mixed liquor and suspended solid, and this is called mixed liquor suspended solid. The portion of MLSS that is actually eating the incoming food is referred to as mixed liquor volatile suspended solid, that is MLVSS. Okay, so this is something I want to explain in this question. I think this is clear now. Okay. Thank you. So the next is, which of the following is not an assumption in activated sludge process modeling? So see, we have microorganism, right? We have substrate. Substrate means the food. Food is organic matter in the polluted water. So we have microorganism, we have substrate, and microorganism will grow and will also die. So the rate with which they are dividing, the rate with which they are dying, the rate with which a substrate is getting consumed, so we have to model it into some equations. Okay, and for that equation we have to have some assumption as well, because this is very complex in nature. So the question is, which of the following is not an assumption in activated sludge process modeling? And we have four options here. Content in the aeration tank are completely mixed. Influent substrate concentration S node is constant. System operate under steady state condition. Microbial solid are present in raw wastewater influent. Which one you think is the right option? Priscilla gave me a D option. Okay. Uh, so Venkateshwar also. So yes, D is the right option, because whenever we are modeling something, we have to simplify the process. So now we are. So again, I'm drawing the same thing. This is the aeration tank that have liquid and microorganism, and the polluted water will come in. Polluted water will have organic matter, so that will be the substrate S node. So content in the aeration tank are completely mixed. Yes, this is the assumption that we have. Influent substrate concentration is constant. So it is not like uh, when like few liter of your wastewater have some different substrate concentration or organic different organic matter concentration, and some of your liter of your polluted water have different. No, we are assuming that whatever polluted water we have, we already have mixed it, and the substrate concentration is very constant. It is not changing with the time. System operate under steady state condition. Yes, so this is, we are applying some equilibrium. We will talk about this equilibrium. And microbial solids are present in raw wastewater influent. No, we are assuming that whatever water we are having, this polluted water, that polluted water do not have the microorganism that will eat that substrate, but we are just having the microorganism in the aeration tank that will eat this organic matter. So here the D assumption is wrong, because we are assuming that polluted water do not have microbial solid that will degrade the organic matter. Okay, so D is the right option. So I'm just reading this. Content in the aeration tank are completely mixed, and that there are no microbial solid in raw wastewater influent. Influent substrate concentration as note will remain the same, and the system operate under steady state condition. And another is solid are wasted from sludge recycle line, and they may be wasted from they may also be wasted from aeration tank. So D option is the right one. Okay, if you want to do the analysis to see the performance of this activated sludge process, that will be commonly expressed as BOD removed per liter of wastewater, BOD utilized per unit mass of active biological solids, reduction in MLSS concentration, sludge wasted per cycle. What do you think? What is the right option? Okay, Priscilla with A, but with the question mark. You are nearby, but not exactly the same answer. Okay, so yes, B is the right option. So what? As I told you, we have polluted water. That polluted water have the organic matter, and how much of this organic matter is being removed, this will be shown by BOD. Okay, but because we do have microorganism, okay, so the first thing is we have to take into consider this BOD removal. So how much BOD we are removing. The second is, but how much microorganism we are using. Okay, so we also have to take into account the microorganisms. Okay, so that's why whenever we are seeing the performance of this activated sludge process, first thing BOD and second thing your microbes. So how much, what mass of microbes you need to remove BOD, or how much, first how much BOD and per mass of active biological solid that BOD has been removed. So that's how performance will be analyzed. Here BOD removed per liter of wastewater. This is not accounting the microorganism. So A is not the right option. Reduction in MLSS concentration. This is absurd. Then sludge wasted per cycle. No, this is not also the option. So B is the right one. Okay. Because I told you we have a steady state condition, and again I'm drawing the same thing. We have a reaction tank that have microorganism and liquid, and we have the wastewater. That wastewater have the BOD. Okay. Then, under steady state condition, the microorganism mass balance in the aeration tank is expressed as inflow is equal to outflow minus growth, inflow minus outflow plus growth is equal to 0, inflow plus growth is equal to outflow, and inflow minus growth is equal to outflow. Yes, B is the right option. Venkateshwara gave me B option. So, yes, I'm also agreeing with B. That is inflow. So, inflow is how much microorganism you are putting into. Okay, so this will be your inflow. Then outflow, because some of the microorganism you have to waste, some of the microorganism you have to waste. Why you have to waste? Otherwise there will be starvation kind of condition, or it may be because we have organic load, so there will be disbalance. It may be that there is no any filtration is going on, so we have to maintain the balance of mass of microorganism. So some of the microorganism we have to add into this aeration tank, but some of the microorganism we have to remove, and constantly we have to create the steady state. Some are being added and some are being removing. So this is your inflow and this is your outflow, but there will be the growth of your microorganism as well. So this will be plus, and that should be equal to 0. So that's how B is your right option. Okay, little bit technical, but try to understand. And if even if you are not able to understand, then let me know, please. So Q is your flow rate. Q is your flow rate. S is your substrate. S is your substrate, or you can say the organic matter. Okay. Then X is your microorganism concentration. So this is the concentration of microorganism. V is your volume. S is your substrate utilization. So, or this is S node. So initially substrate, how much substrate or organic load it had, and this is how much substrate we have now in the aeration tank. And how, so this is kind of BOD. So initially BOD was higher, let's say it was 200 mg per liter, but here because some degradation is being happening, then uh, uh, then our substrate concentration will be lesser. So BOD will be, let's say, now 50 mg per liter. Okay, so this is your substrate. Then uh, okay, so what will happen, some substrate with some flow rate will come into this aeration tank. Okay, then in that aeration tank, after degradation of organic matter, your substrate will be reduced. Your substrate will be reduced because we have microorganism concentration. Then there will be some growth and the decay of your microorganism, and even that organic matter that we have degraded into the simpler substance will be deposit here, will deposit here. And because that have some organic matter and also have some microorganism, so that will come under your sludge part, and that some of your sludge will be given back to your aeration tank. So this is something, rate of inflow of microorganism into the system, rate of outflow of microorganism from the system, plus net rate of cell growth in the aeration system will be equal to 0. So if we are having the equation here, so this is your flow rate, this is your flow rate, this is your microorganism concentration in influent, and we are having the assumption that we do not have microorganism, but this is your inflow. Okay, this is your inflow, this is your outflow of microorganism, and in outflow some of the some of your microorganism will go into waste. So this is concentration of microorganism in waste sludge, that will also have some flow rate, and this is out of your total flow rate, the remaining after wastage, and that will be your, and this x is your, xe is your concentration of microorganism in effluent, so the water that is coming out, and this is your growth rate, and that will be equal to 0. So based on that we have numerical question as well, but just keep in mind, inflow of microorganism, the inflow rate of microorganism minus outflow of my outflow rate of microorganism plus growth rate, that will be equal to 0. If you have any problem with this equation, you can let me know. Initially we had microorganism concentration x node, then we will have xe, then we in the waste we will have the xr. These are the microorganism concentration. This is your flow rate, initial flow rate, then the flow rate of your waste, the remaining flow rate, and this is your growth, so this will be equal to 0. And in the growth rate, we have this rg, and this rg will equal to minus y rsu minus kdx, and here y is equal to yield coefficient, rsu is the substrate utilization rate, the rate with which substrate or organic matter is taken up by the microorganism. So this is your substrate utilization rate. KD is decay coefficient, because in the growth we also have to consider. So this is your growth rate and this is your decay rate. And then this will be your net growth rate. And X is your concentration of microbial mass. So this part can be expanded from this one. Okay. Uh, okay. So, in activated sludge mass balance equation, the term Q minus QW XE plus QW XR represent what? So, we have four options here: net microbial growth in the aeration tank, inflow of microorganism into the system, outflow of microorganism from the system, and substrate utilization. Priscilla is very fast to give the answer, and he gave me C answer. Okay, so yes, we already have discussed about this part. So let me show you again. So this is your inflow, this is your outflow, and this is your growth rate, and that would be balanced, and that would give you the zero. So that is the steady state condition of microorganism, right? So we were talking about this second term, and this second term is your outflow of microorganism from the system. Okay, so we talked in growth rate, it was yield coefficient, and yield coefficient in activated sludge model refers to, we have four options here: ratio of biomass formed to substrate utilized, fraction of mlss that is volatile, concentration of microbe wasted per day, ratio of influent to effluent substrate concentration. Yield coefficient. What do you mean by this yield coefficient? Why it is important? Any guess about this? Not D. Okay, so let me tell you. So the answer will be A. Yes. So answer will be A. So this is whenever organic matter of your polluted water is taken up by the organisms, right? So how much, and this organic matter is your substrate. Organic matter is your substrate, and because whenever microorganism will get some substrate, microorganism will divide and will increase the population, will increase the population. So this is how much biomass is formed, how much microorganism is formed per substrate utilization. Okay, and substrate is your BOD, right? BOD per BOD per liter, let's say, or mg per liter. So how much substrate or organic matter we should have in the polluted water so that microorganism can divide and can also replicate, and what is the ratio between this? The biomass formed, so microorganism will grow in the presence of substrate. So how much substrate is utilizing to form the microorganism? So this will come under the yield coefficient. So A is the right option. And so this will be, so biomass formed, as I told you, biomass will be this is volatile suspended solid. So we are having the unit of these microbes as the volatile suspended solid. So this is your biomass formed, and substrate utilized. Substrate is the organic matter, and organic matter we are having the unit of organic matter in the form of BOD. So the unit will be mgvss upon mgbod5, and most of the time the yield coefficient is zero point 0.4 to zero point 0.8. Okay, so another, because right now we are talking little bit about the engineering or technical part in activated sludge. So we have one terminology that is known as the hydraulic retention time, and this is again important. Every term whatever we are discussing, either it is yield coefficient or your substrate concentration, microbe concentration, the steady state, that equation, everything is important to balance out and to increase the efficiency of your BOD removal, right? So that's how we are learning these terms. And the one term is hydraulic retention time, and you have to tell me what is the formula for hydraulic retention time. So first you have to understand what does it mean. So it is Vx upon Q. So V is volume, X is your microbe concentration, and Q is your flow rate. V by Q, Q minus Q, Wxc upon Vx, Q upon V. Okay, so Dia Priscilla gave me a B answer. Venkateshwara, the right answer will be B only. Let me show you how. So first you have to understand what do you mean by this hydraulic retention time. So this hydraulic retention time is the average time that wastewater spends in the aeration tank. So this is just the time. What is the time, average time, so that that wastewater is spending in that aeration tank. Okay, so because here the unit will be either day or hours, so this will be volume of your aeration tank upon your flow rate. So because here we are not talking about microorganism, we are just talking about the wastewater and how much time the wastewater will be in aeration tank. Okay, so this will be based on just the volume of aeration tank and the flow rate of your wastewater that is coming in the aeration tank. So that's why this will be equal to V by Q. Okay, one very important equation is monod kinetic equation, and this is very important. Which equation relates substrate utilization rate to biomass and substrate concentration using monad kinetics? Because just see, you have microorganism, right? You have microorganism, you have organic matter, you have volume of your wastewater, and this microorganism is depend on this organic matter that we have in the wastewater. So how much this organic matter we have, then how much of this microbes will take this organic matter, then based on that what will be the growth of microorganism, what will be the decay rate of your microorganism. This will come under one equation, and that equation is known as the monad kinetics equation. And you have to tell me which one is the right equation. Let me see who gave me answer. Priscilla B. Okay, and Venkateshwara C. But I will agree with this B option, and let me show you why. So, so this equation is known as monod substrate utilization rate equation, and this equation says that the rate at which food is consumed. So this will depend on how much microorganism we have, X, how much food is available, S. So this is my organic matter. How good the microbes are at eating it. So this is like the utilization rate as well. So it may be the case that some of the microorganism are not utilizing the organic matter as efficiently as another other microorganism can have. Okay, so we have to see the capacity or efficiency of microorganism as well, to which they are eating that organic matter. So this will be under K. And how sensitive they are to low food condition. So will they die, will they grow, will they be sustained? So this is also, so this is something, the behavior of your microorganism. So based on that only you will decide how your food will be consumed. So this will be substrate utilization rate. This will be depend on microorganism, the substrate that we have, the efficiency of microorganism to eat that substrate, and how sensitive are they when we do have low organic matter in the polluted water. Okay, so that's how, this is your equation for the substrate utilization rate. Okay, so we have RSU, right? Uh, thank you so much, Venkateshwara. So this RSU, so rate at which substrate is consumed by the microorganism, and here negative sign is because substrate is decreasing with time. That's why we do have negative sign, and the unit will be mg substrate uh, per liter and day. Then we have 1K term, right? And this K is known as maximum specific substrate utilization rate. So this will represent the highest rate at which microorganism can consume substrate per unit biomass. Okay. Then the next terminology is biomass concentration. You know about this, how much microorganism we have in that substrate. So these are eaters in the system. So mg per liter. And the substrate concentration, how much organic matter, and that will be in the form of BOD and COD is available in the aeration tank. So that will be mg per liter. Then we also have Ks, that is known as the half saturation coefficient. This is the substrate concentration at which the substrate utilization rate is half of its maximum. This is very important, and just keep in mind this one only. Okay, the another terminology about this activated sludge processing is mean cell residence time. So what does it mean? So we have four options here. The time substrate remain in the system, the average time microorganism remain in the system, the ratio of substrate to biomass concentration, and the maximum growth rate of microbes. We have another terminology, that is a mean cell residence time. What does it mean? Any guess about this? Mean cell residence. From cell only you can tell. Okay, so it is time, right? It is time. It is not the rate. So from that time hint, I think you can give me the right option. Yes. So let me see. Priscilla gave me B, and then Venkateshwara first gave me D, then A. No, the B answer will be right. So this is also important. So the average time microorganism remain in the system, either the time is 2 hour or 3 hour or 4 hour, because based on that also it will be decided how much organic matter will be degraded or how much organic matter will be consumed by the microorganism. So mean cell residence time, how much time the microorganism is living in the aeration tank. Okay, so that is also important for us. So this will be the average time microorganism remain in the system. So this is also known as MCRT, and this is the average time the microorganism remain in the system, either it is in aeration tank or it is in secondary clarifier. and this is also known as sludge age and the solid retention time, SRT. And how we can have that in the formula. So this is the mass of solid in aeration tank and mass of the solid leaving the system per day. So this the unit of this mass of solid and mass of solid will be cancelled out. This per day will go up, and that's how this residence time will be in time, in days or in hours, right? And this is in per day, so this day will go up on the numerator and this will be cancelled out. So this will be Vx. So this is your volume, this is your microorganism concentration, then this is your flow rate, and this is your microorganism that is leaving the system, so wasted, W is wasted, and this is QE, that is the affluent flow rate, and this is affluent microorganism or solid concentration. So this is the formula of your mean cell residence time, MCRT. Okay, because we know that whatever organism we have, that organism will also die. Okay, and at what rate they are dying, this is also important for us to see the efficiency of this activated sludge, right? So, for that, we have one terminology that is known as the decay coefficient. Decay coefficient increase sufficiently. If increase sufficiently, which of the following is most directly affected? If the decay coefficient, if organisms are dying significantly, then which of the following is most directly affected? Substrate concentration, biomass concentration, hydraulic retention time, and influent flow rate. Okay, so Dia gave me B option and Priscilla also gave me B option. So yes, B option is the right one because we are talking about microorganism, and this decay coefficient is for the microorganism only. So B will be the right option. I think I have explanation also. So I'm having a lot of equation as well, because otherwise whenever you will see that equation, that would be very complex for you. That's why I put that equations into your MCQs, and in such a way that each equation you can understand in the form of MCQ. So okay, so if it is the decay coefficient, so decay coefficient is the decrement or like the change in the microorganism dx per time. So this will be equal to mu x minus kdx. So this is your specific growth rate and this is your microorganism concentration. So this will be your growth rate, right? And this will be your decay rate. And whenever we are subtracting it, then we are getting the change in your microorganism per time. So change in the biomass of microorganism per time. So this kd is your decay coefficient. Okay, so uh, kd, that is the endogenous decay rate coefficient. This represent the rate at which microorganism die or lose activity in the activated sludge process. So I think this equation is very simpler. If I give you numerical on this, I think you can solve that. I'm expecting that you will solve it. This one is the explanation why substrate concentration is the right option, but I don't think that there is any need. Okay, we also talked about saturation constant in steady state equation, right? And this is Kx. For domestic wastewater, you have to tell me the typical value of half saturation coefficient for domestic wastewater at 20 degrees Celsius, and you have to tell me the range. But first, you have to remember what was that half saturation coefficient. Venkateshwara is fast enough to give me. answer, but D is the right answer. And let me show you. First, you have to understand what is this half saturation coefficient. So, we have talked about this monad kinetics, right? And in monad kinetics, we had this mu. Okay, and this monad kinetics we described to tell about the microbial growth. And here we have this ks. This ks is the half saturation coefficient, and let me tell you the definition of this. So this is the substrate concentration at which the microbial growth rate is half of its maximum. So this will be the concentration of your substrate, but when the microbial growth rate is half of its maximum. So then what will be your substrate concentration? It is simply means a measure of how efficiently microorganism can use the substrate. So that will define by the ks. Okay, as I told you about f and m ratio, so you have to tell me when what should be the f and m ratio, so that your and according to which what would be the efficiency to remove that bod or to remove that substrate or microorganism, sorry, uh, organic matter from your polluted water. So we have high and low food and microbe ratio, and then high, this is your age, sludge age. This is your sludge age and the efficiency. So Dia gave me B, then Venkateshwara also gave me B option. Okay, so yes, B is the right option. As I told you, the efficiency to remove the BOD or to remove the organic matter will be inversely proportional to your F and M ratio. So more of the BOD will be removed when your F and ratio will be low. When your f and m ratio will be higher, then bod removal will be reduced. So based on that, if your removal efficiency is higher, then bod f and m ratio should be low. Okay, and when your food and microbe ratio will be low, lower means what? We have less food and more microbes. Okay, so it means we do not have much food for the reproduction or to divide the microorganism into two, or to divide or for the replication. So it means more of the microorganism will be as it is in the aeration tank. It means the age will be higher, otherwise it will be divided into two when food will be more. Okay, so it means whenever you have low food microbe ratio, then your age of your microbes will be higher because they are not dividing, they do not have enough food to divide. And whenever you have more age of your microorganism, then your efficiency for removal the bod will also higher. That would be near to 90 to 95%. So that's how B is the right option. Just see here, whenever we have high food microbe ratio, at that means we have plenty of food, less biomass age, because that will divide fast. Whenever they will divide fast, the sludge production will be higher, and it means the treatment efficiency will be lower. Whenever we do have low food microbe ratio, then there will be less food per microbe. It means they are not dividing. They are not dividing means we do have sludge age that is longer. It means the sludge production is not higher. It means stable or efficient treatment, that will be 90 to 95%. And that's how your sludge age, and your FM ratio are inversely related. So I think this is clear now. Okay. The one thing about your activated sludge is sludge volume index. So sludge, you have to tell me what do you mean by sludge volume index. Volume of sludge after 24 hour upon MLSS concentration. Volume of sludge after 30 minutes divide by MLSS concentration. Mass of sludge per liter of wastewater. Volume of water per gram of sludge. Okay, so Dia and Priscilla both gave me a B answer. So yes, so this is the volume of sludge. So I am expecting that you are understanding what is sludge. So sludge is whenever you have microorganism in the aeration tank and some organic matter is coming in the polluted water, so there will be some degradation. Some of your microorganism and some of your organic matter will be settled down, so that will create some muddy like condition, and that we have to remove. That is sludge. Okay, and we need to, because that also have microorganism, then we can recycle this sludge and we can again put into the aeration tank. Okay, so this is something sludge, and we know that the sludge should have some consistency. It should not be very hard, it should not be very diluted, because whenever the sludge is very diluted, it is very hard to treat that sludge also. So this is something, we are having the wastewater, then we are having very diluted sludge, and again the problem will be how we can remove that bulk amount of sludge. So this is very important to have a particular consistency of your sludge. That's why this sludge volume index is very important. So how much volume of sludge we will have after 30 uh, minute upon VLSS concentration. So how much concentration we had of microorganism in the liquid. So that's how B answer will be right one. So sludge volume index measure of how well sludge settle in the secondary clarifiers. Whenever we have sludge volume index between 40 to 100 ml per gram, then this is known as good sludge. If it is more than 200 milliliter per gram, then this means it is the poor sludge. So it will create some bulking. And whenever we do have bulky sludge, then this bulky sludge is because of some microorganism that do not settle easily. So it will be very difficult for us uh, to remove this effluent to sludge separation. So because we know now, we do have polluted water, we have aeration tank, and some the clean water will go uh, go on. So, and because we do have suspended microorganism, if we are not able to uh, if we are not able to separate this water from your microorganism, then this means this is the bulking sludge. We are not able to do the separation, and this will be very difficult for us uh, to to get or to extract the clean water, right? So, the cause of high SVI may be variable food and microorganism ratio, high concentration of heavy metal, and it may be due to the temperature. And how we can prevent this bulking? Either we can have this proper pH control, we can give more oxygen, more air to the aeration tank, and we can also add some chemicals to have some particular consistency of this sludge. Okay, Which of the following indicate a bulking sludge in an activated sludge process? Equal to 50 milliliter per gram, 90 milliliter per gram, 120 milliliter per gram, 220 milliliter per gram. When the sludge will have that bulky problem. Okay, so Dia gave me option B. Okay, so yes, this is whenever we do have more than 200, as I showed you right here. Um, Here, we talked about this. The good sludge is when we do have SVI, the range is from 40 to 100. But when we have more than 200 milliliter per gram, then this will create the bulking. So this is like in 20, in 1 gram of microbes, in 1 gram of microbes, you have 200 milliliter of water. So it means it is like very difficult for us to, but it should be less water per liter of your microbes, per gram of your microbe. So this will create the bulky condition. Okay, so because we have learned some terminology, so I have one numerical. I do not have MCQ like this, but I just want to make you understand how we can solve this. And I think now every terminology is very clear related to your activated sludge. So in activated sludge process, you want to treat the wastewater, the flow. So this flow of your wastewater, that is Q, is equal to 520 meter cube per liter, having soluble BOD. So this is your substrate or microorganism. So BOD of 230 mg per liter. The concentration of soluble BOD escaping treatment is 20 mg per liter. So you are removing this BOD from 230 mg per liter to 12 mg per liter. So this much. So this is the BOD that we are removing from the wastewater. Then this is the Y. Yield coefficient is given, that is 0.4. Then we have the K. Then we have KD, that is the decay coefficient. This K is, I think, growth rate. And then we have KS. So everything we have learned, right? And the concentration of your mixed liquor, volatile suspended solid. So this is the microorganism X. This is also given 2000 mg per liter. And what they expected us to compute: the treatment efficiency, mean cell residence time, hydraulic retention time, the volume of the irrigation tank. I think each of this terminology is very clear to you. It may or may not be that you are remembering the formula for this, but what I'm expecting from you is that the terminology is very clear to you. Okay, so if this is the case, then the efficiency is because as I told you, BOD removed from 230 to 12. So efficiency will be 230 minus 12 upon 230. So it means the BOD removal efficiency is near to 95%. Okay. Then you have mean residence time. So mean residence time we can calculate using this formula, and each of these values are given. So, and as I told you, mean residence time is uh, how much of the time the microorganism will be in the system. So this will be this value. Then we also had hydraulic retention time. So how much of the time wastewater will remain in the aeration tank? So using that formula you can also calculate this. And then the volume of your aeration tank, we also have learned this formula, right? Q is equal, this was your retention time, and then V upon Q. So from there we can calculate the volume of your aeration tank. So this will be this much. So I think the terminology is very clear, but it may be that you are not remembering the formulas, but it's okay if even you are understanding the concept of activated sludge processing, right? So this was the part of your activated sludge process. Now we are moving to the next technique. That technique is known as the trickling filter. In activated sludge, we had the aeration tank in which we had the liquid, and in that liquid we had the microorganism, and this is the polluted water. Then some effluent will go on after degradation in this aeration tank. This was in activated sludge. In trickling filter, it is something we do have a layer of your microorganism on some surface. So this is your surface. It may be this surface is of stones, let's say, and on that we have the layer of microorganism, and then the wastewater will be trickled into that, and then then the clean water will be at the like the polluted water will have to cross this layer of the microbe, and then whenever it will cross that, the so organic matter will be trapped by this microorganism, will be degraded, and the clean water will be passed to the bottom of it. Okay, so this is, we are having the fixed microorganism layer. Here we had the suspended. Okay, so if this is the case, then this will come under the trickling filter. And now we will have some question on trickling filter. After activated sludge process, the second most commonly used biological waste treatment process is activated sludge, septic tank, trickling filter, anaerobic digester. What do you think? Which one is the second most commonly used biological waste treatment process? Okay, Priscilla gave me C answer. Yes, obviously we are talking about trickling filter. Then yes, after activated sludge process, the trickling filter method is the second most used method to remove the BOD of your wastewater. Let me show you. This is what I was talking about. So this is your microorganism layer, right? And the wastewater will be sprinkled. Then the wastewater, then after treatment, then the clean water will be settled here, and this is your outlet from where the clean water will be go on. So, and here we will have some stone or a lot of things on which your microorganism will be attached to. It means microorganisms are not suspended in the solution, but they are attached to some surface, right? So this is the difference between activated sludge and the trickling filter. And this is the another way by which we can understand. This is your media. This is your media. In that media you have microorganism, then again trickling filters. You have filter that will give the wastewater to this media that have the microorganism, and then it will give you the water, clean water, and that clean water will come into that clarifier. Some sludge will be removed, and then this will give you the treated water. Okay, the one problem with the trickling filter is that whenever we do have excess of biofilm and that will detach due to microbial decay, this process is known as what? Shedding, slogging, settling, or stripping. Venkateshwara and Priscilla and even Dia. Okay, so everyone gave me a B answer. So yes, this is slogging. As I told you, we have some media, and into that media we have some microorganism attached to it. So it may be that if we do not have enough organic matter, or if you see, like this is the part where the oxygen may be less present, because this is not in the connect with air. Okay, so let's say this is your air, right? So this part is not attached to the oxygen. So what will happen if they are not getting attached with the oxygen? Then there would be the decay rate. They do not have the growth. So these will be died, and this part have to, because they are dyed, then no longer they can attach to the substrate, they have to detach, and this detaching is known as the slogging. So just see here, trickling filter are biological treatment system where microorganisms form a biofilm on the media surface. Over time, as biofilm grow thicker, the inner layer may become starved of oxygen or nutrient. Waste product may accumulate in the biofilm. Shear force from wastewater flow or weight of upper biofilm layer can cause part of biofilm to detach or peel off. And this detachment of biofilm is called slogging. This logging can be normal, and this is also continuous process, because there will be always gradual detachment of your biofilm, and this will maintain active layer of microorganism, because this is removing your decayed or died microorganism. But whenever we do have excess or sudden slogging, this may occur when biofilm becomes too thick or hydraulic stress is very higher, and it can cause a shock load to downstream unit. So slogging is a problem that we have in the trickling filter, and that's why it doesn't come on that first popular use wastewater treatment process, but it is second most. And then the slogging have advantage and disadvantage as well. So if we are talking about advantage, so it will maintain biofilm activity, so it will ensure that active microorganisms are also available at the biofilm surface. It can prevent cloggings. So continuous slogging reduce the risk of filter media get choked by too much biomass. Feed secondary clarifier. Slugged biomass become the part of suspended solid in effluent, and this is removed in secondary clarifier, and it is the indicator of filter health. So whenever we do have normal slogging, it means the filter is in healthy condition, but whenever we do have excess slogging, it means there is some problem or issue that we have in the operation. Okay, as I told you, microorganisms are attached on some media. So there is the thickness of this biofilm. So what typical thickness of biofilm we have in the trickling filter? 1 to 10 micrometer, 100 micrometer to 2 mm, 2 to 5 centimeter, and more than 10 mm. Dia and Priscilla both gave me B option. Okay. So yes, the biofilm thickness is near to 100 micrometer to 2 in the trickling filter. What condition may develop at the base of thick biofilm? Aerobic zone, facultative zone, anaerobic zone, anoxic zone. Okay, so Diya and Venkateshwara both gave me answer C. So yes, this is the anaerobic zone because as I told you, we will not have direct connection with the air. So this there will be the condition where we will not have enough oxygen, and if there is not enough oxygen, it means we will have microorganism that will be present here in the absence of oxygen. So this will be the anaerobic zone. So aerobic zone is the zone where oxygen and oxygen dependent microorganisms are present. Facultative, where both aerobic and anaerobic condition can be happen. Anoxic is the organism will be aerobic, but it may be that we do not have oxygen presence here. So that's how this uh, microbes have to be died. So this will be the anoxic condition, but here this is the anaerobic zone. Trickling filter using synthetic plastic packing media with high void space are called high rate filter, uh, roughing filter, super rate filter, extended filters. So we are using packing media on which we grow the microorganism, and that packing material, packing media may be made up of synthetic plastic, and that would have a higher void space so that filtration can be happening. There is no clogging. So you have to tell me, then such kind of filter will be known as what? Okay, so Dia gave me C, Priscilla A, not A, but this is known as the super rate filter. These are not the high rate filter, but whenever we are using synthetic plastic that have high void space, high space, then this will come under super rate filter. Okay, so the next question is, a high rate trickling filter is characterized by low organic and hydraulic loading, high organic and hydraulic loading, synthetic media with high void space, partial BOD removal only. Priscilla gave me B. Yes. So this is high loading and hydraulic loading. So high organic means we can have the we can have the wastewater that may have higher organic loading and hydraulic loading as well. So this will come under high rate trickling filter. So okay, so we were talking about this the difference between low flow rate, high flow rate, sorry, low rate filter, high rate filter, and super rate filter. So if we are talking about the hydraulic loading, so how much of the polluted water we can have in that trickling filter, the volume per meter square per day. For the low rate filter it is 1 to 4, for higher it is 10 to 40, for super it is 40 to 200 meter cube of water per meter square area per day. If we are talking about the organic loading in that particular volume of wastewater, how much BOD we can have? So in low rate we can have BOD 0.08 to 0.32 kg BOD per meter cube per day. And in high rate and super rate it can be more. It means whenever we have very dirty water that have higher organic loading, that can be removed efficiently using high and super rate filters. Depth is higher for the super rate filter as comparison to the low rate filter. Recirculation ratio is 0 here. For the high and super we can recirculate, and this is 1 to 4. Then the filter media in the low rate filter, it is made up of rock and slag. In the high rate filter it is made up of rock, slag and synthetic material. And for super rate filter it is just made up of synthetic material. So I think one question that we had, and you gave me a option, that a option may be right, but because that was the high rate filter, but along that we can have also rock and slag in high rate. But super rate filter is just made up of synthetic material. That's why I gave you super rate filter, replacing this high rate filter in that MCQ question. Okay, so if we are talking about the flies that we can have in the filter, in the low rate filter, we can have a lot of flies. In high and super, we will have a few flies. Then, if we are talking about the slogging process, then it is intermittent in lower, but it is continuous in high and super. Effluent quality after this trickling filter, after removing the BOD, what kind of treated water we will have at last. In the low filter we will have usually fully nitrified. In high and super rate filter we will have nitrified but at low loading. And BOD removal is higher in low rate filter, but it is 65 to 80 for super and high rate filter. So the advantage of high and super is just that they can have high organic loading, and even the hydraulic loading may be higher. But if we are talking about the low filter, then the removal efficiency is more as comparison to high and super rate filter. Okay, because we are talking about the technical things of the treatment processes, then we have one SE in your trickling filter performance prediction, and that SE refers to what? We have influent substrate concentration, affluent substrate concentration, solids concentration in sludge, specific surface area. SE. From this first word and second word, I think you can guess something about this. Any guess? What does this SE means? Okay, Venkateshwara gave me B. Yes. So this is the effluent substrate concentration. Uh, so the thing is, we have trickling filter, right? And this is media. Then from here we have the wastewater, and this is your treated water. So how much substrate concentration, or you can say the BOD concentration we had initially? So this is influent substrate concentration. Influent. Then the substrate concentration after this filtering. So this will be the BOD that we will have in the effluent or treated water. So this is the substrate or BOD or organic matter that we will have after treatment. So that's how this is the effluent means treated water, substrate means BOD or organic matter concentration. So based on this, how much concentration of organic matter we had initially and how much we have right now, based on that we can tell about the performance of your trickling filter, because BOD uh, should be removed um, efficiently. So this is the formula. SE is the concentration of settle effluent from the filter. So how much BOD we have after filtering, how much BOD we had in the wastewater. K is the empirical rate constant. A is the cross sectional area of filter. AS is the specific surface area of filter. This will be surface area of filter upon volume. Q is your wastewater flow rate, and N are the empirical constant, and L is your filter depth. So based on that, you can tell the performance of your trickling filter, because this is the BOD after treatment and this is the BOD before treatment, and this is how we can calculate the performance of your trickling filter. Okay, in that formula only, we used specific surface area AS of the trickling filter, that will define as what? Cross sectional area upon filter depth, surface area of filter media upon volume of filter, wastewater flow rate upon influent concentration, and hydraulic loading upon organic loading. So I'm having answer. Dia gave me B. Priscilla also gave me B, and Venkateshwara. Yes. So you people gave me B answer. Then I also agree with this. So here only we talked about this, right? So A is the specific surface area of your filter, and that would be the surface area of your filter upon volume. So from that terminology only, we had the options. So from that, the B option will be the right one. Okay, so we had monode kinetics in activated sludge process, right? In which we tried to explain how much substrate will be utilized, how much organism will be present, what will be the decay rate, what will be the growth rate, what would be the efficiency of your microorganism to take or to consume that substrate. So everything can be modeled into activated sludge process, but we do not have kinetic model for trickling filter. But why? So we have four options here: lack of empirical constants, unstable slime layer and unpredictable hydraulics, too many variable in influent concentration, large variation in filter cross sectional area. What do you think? What is the right answer? Okay, so Priscilla gave me very quick B option. So yes, I also agree with this, because here the slime layer is, we talked about the slogging condition, detachment of your biofilm due to some hydraulic shock, or due to, because there is anaerobic condition at the bottom of your media, so that microorganism will be starved, will not have sufficient oxygen or sufficient food, so they have to be detached. So this was the slogging condition, and because of that condition, because that is very continuous, so it is not not very easy for the engineer to develop the kinetic model for the trickling filter, just because of this unstable slime layer and unpredictable hydraulics. Okay, again, because we have learned some terminology in this trickling filter, then we have one numerical, and then we will move to the next technique. So here the depth of low rate trickling filter has a diameter of 43 meter, The hydraulic loading is 0.13 meter cube per second. Influent and effluent BOD is 255 and 20 mg per liter, and the unit operate at 27 degrees Celsius. Empirical constant are also given. M is equal to N is equal to 1, and K25 is also given. Then you also have the porosity, that is given 0.6, and a sphericity zero point 0.9, and geometric mean size of rock. So this is the dimension of the media they are giving. This is the 80 and they need to calculate the depth of your low rate trickling filter, and the one formula we already have explained. From that formula only, so this is the formula at the top we already have explained. From that formula, first we will calculate specific area. If we do have the specific area, then we will put that into the specific area, and we can get the depth when we do have the volume and all. So this is, I think, like the first formula we already have explained, and the next, these formulas are very basic based on your dimensions. Okay, so we have covered activated sludge process. We have covered trickling filter. Okay, and the techniques, some terminology related to that techniques. The next is upflow anaerobic sludge blanket reactor, known as UASB, and we have few questions on UASB. But before that, you must have to see the principle of this UASB. So this is something influent in the bottom of your that container. The polluted water will come into that container. Okay, then because this is anaerobic condition, so we are not giving the oxygen. We have the microorganism that will survive in the absence of oxygen. So in the absence of oxygen, organic matter will be degraded. Okay, so whenever this will happen, so this will not be the carbon dioxide or the water that will be that would be the end product, but this will be some biogases that will be removed. Okay, so here we will have biogases that will be removed from the top, and from the right hand side, top right hand side, we will have the effluent. Okay, so here the main thing is that because we are using anaerobic condition, we have the microorganism that will survive in the absence of oxygen, so the sludge will be very low in that condition as comparison to the aerobic activated sludge process, right? So here, whatever organic matter we will have, that will produce 10% sludge but 90% methane production, and methane we can use as a biofuel, right? So this is the advantage of being the anaerobic sludge blanket in place of activated sludge, because activated sludge is giving you too much sludge. But here in anaerobic sludge blanket, it is giving you just 10% sludge but 90% methane, and that we can use as a biofuel. So okay, here also we have solid retention time. It means microbes that will be there in that container for temperature above 20 degrees Celsius. So what would be the typical solid retention time, SRT, in a UASB reactor? 5 to 10 days, 15 to 20, 30 to 50, 60 to 90. Dia gave me a C answer. So this is 30 to 50 days. So 30 to 50 days, microorganism that are anaerobic in nature will be there in that UASB reactor. Okay, average concentration of sludge. So, how much sludge it is producing in a UASB reactor? This is close to what? 7 kg per meter cube, 70 kg per meter cube, 700 kg per meter cube, and 1000 kg meter cube. Again, Dia gave me B option. So yes, so this is how much sludge it is producing. So this is 70 kg per meter cube. Okay, so in that UASB, we also have sludge age, and that sludge age can be calculated as mass of sludge wasted per day divided by mass of MLSS in aeration basin, total mass of MLSS in aeration basin upon daily mass of TSS in effluent, mass of effluent SS divided by mass of sludge wasted per day, and total MLSS upon reactor volume. So let me see the answers. Okay, so Dia gave me a B option, and yes, so this is total mass of MLSS. We already have talked about this MLSS. This is mixed liquor suspended solid. So this is microorganism in the liquid, and divide by total mass of total suspended solid in effluent. So how much microorganism we have in the influents. So this is your sludges, and but the thing is, what is the significance of calculating this sludges? So this will tell how long the biomass is exposed to the influent. Influent is your wastewater, right? So how long that wastewater will be in touch with your microorganism, because microorganism will degrade the micro organic compound or organic matter that we have in the wastewater. So more the contact or more the time we will have this connection, then more of this BOD will be removed. So often in anaerobic reactor where the influent feed is a limiting factor for growth, simpler does not account for biomass leaving the system. Okay, so here also we do have MCRT, that is mean cell residence time, and this is different from sludge age because it consider what? Only influent TSS load, sludge wasting and effluent SS losses, aeration tank volume, and influent BOD concentration. So how this MCRT is different from sludge age? We already have gone through this sludge age, right? So this is your sludge age, and we have learnt about this MCRT, that is how much time the microorganism will remain in the system. So this will be the MCRT. So how it is different from your sludges? Any guess about this? Any guess? Okay, so this is sludge wasting and effluent SS losses. Let me show you the formulas. So for MCRT, this is total mass of mixed liquor suspended solid in reactor divided by mass of sludge wasted per day plus mass of suspended solid in effluent per day. So here this is true microbial age, and that will account all biomass losses. Either it is in the waste or that will go with your treated water. So that's how this is your actual microbial age. And just see here the difference between this. So in the sludge is this is MLSS divided by TSS, and it is not accounting the biomass that is living. Okay, and that's why typically that sludge is used in UASB, but this MCRT, this is MLSS divided by the wasted sludge plus effluent suspended solid, and here the biomass that will be left from that reaction tank will also be taken into account, and this is accurate microbial age in aerobic and anaerobic system also. Very simple numerical. If influent BOD is equal to 350 mg per liter and BOD removal efficiency is 80%. So, what is the BOD removed? How much BOD is removed when BOD removal efficiency is 80%? So, it will be 80% of 350 mg per liter because the removal efficiency is 80%, right? So 80% of 350, 80 divided by 100 multiply by 350, that will give you the BOD that has been removed. So this is something influent BOD, that was the 350, removal efficiency 80%, so 80% is 80 upon 100, so that will give you 280 mg per liter. Okay, if you have influent TSS 385 mg per liter and volatile suspended solid 260 mg per liter, so what would be your ash content? Very easy. Total volatile ash. So total is equal to volatile plus ash. So ash will be equal to total minus volatile. So this will be what? 385 minus 260. What would be the value? 385 minus 260. So Dia gave me C answer. Venkateshwara also gave me C answer, but this is near to 70. Let me, okay, so sorry. You gave me right answer, but I think I marked the wrong. So yes, your answer is right. So this will be C, but somehow I clicked to A. Okay, so we already have talked about this activated sludge, then trickling filter, and then UASB, and now the remaining part is phytoremediation and phycoremediation. These are very easy topic, like no technical thing into that because this is purely ecological based. Okay, so there will be no trickier question about this phytoremediation and phycoremediation. These are very easier. So phyto means, what do you mean by phyto? Phyto means plant. Remediation means we are treating something. So if we are treating something using plants, then this will come under phytoremediation. So for example, if you have polluted air in your room, then you are like you have some uh, you have some plants that you can grow inside your room so that air can be purifier. Okay, so this is something we are remediating the air using plants, so that will also come under phytoremediation. If we do have wastewater, if we have, let's say, after mining the land get degraded. Okay, the land may have heavy metals, the land may have different toxic material that we may have, but if we will grow some kind of species on that area, then that species will take up that toxic metal or toxic things into it, in the roots, in the stems, or in some form, in such a way that it can extract that toxic metal from that soil, and it can remediate that soil. Okay, after mining, let's say. So this will come under the phytoremediation. So which of the following best describe phytoremediation? Removal of contaminants using microbes only, cleanup of contaminants using living plants, chemical neutralization of pollutant in soil, thermal treatment of hazardous waste. Very simple. Venkateshwara gave me B option. So yes, answer is B. Yes, Priscilla also gave me B. So this is the cleanup of contaminants using living plants. So let's say if we do have mining of copper or zinc or mercury or cadmium, so that degraded land may have some concentration of that heavy metal. Or for example, if we had some industries and that industry was based on some heavy metal, so that area will have a huge amount of heavy metal. So we can have some specific plant that we can grow in that area to remove that heavy metals. So for example, if we want to remove chromium heavy metal, so we can use plants such as smooth water, hyssop, Indian mustard, rapeseed plant, tape grass. So likewise, we do have a lot of plant species we can use to remove different kind of heavy metals. Okay, so this is the mechanism how plants can help to remove that heavy metal. So this can be by phytodegradation. So whatever organic compound or whatever inorganic compound it is taking from the soil, it can be degraded by the plant. So this will be the phytodegradation. Phytovolatilization, it can take up from the root, from the soil, and it can volatile it. It can extract that let's say heavy metal into the air. Okay, it can diffuse into the air. So this will be phytovolatilization. So it will volatile that or compound. Then phyto extraction means it will take up that and it will be in either in root or either it will be in stem. So this will be the phyto extraction. Then phytostabilization, it can be that it can fix that. Okay, so that it will be insoluble. It will not be it will not exploit the soil property, so that means it is giving to stabilize this. So this will be the phytostabilization. And one is phytostimulation, very similar to phytodegradation. So these are different processes by which a plant can remove or extract some of the heavy metal or some another hazardous metals or compounds. Okay, so phytoremediation can be effectively used to treat all of the following contaminant except heavy metal, pesticide, landfill leachates, and radioactive isotope. So okay, so Venkateshwara gave me D option, that is radioactive. Priscilla also gave me the same D. So yes, using plants we can remove heavy metals, we can remove pesticide, we can remove landfill leachates, but this is very difficult to remove radioactive isotope using phytoremediation. Okay, which of the following processes prevent heavy metal ion from entering the cytosol? So, cytosol is under the cell, or you can say under the there is one organelles into the plant cell that is known as the cytosol. And there is a one process by which plant can prevent that this metal ion should not go inside that cytosol. So this process will be known as what? So this will be known as the exclusion. Okay, so exclusion. Chelation is there is complex structure with of some compound with the metals, so this will be the chelation. Immobilized means we are stabilizing this so that it will be insoluble, or we the mobile phase of your heavy metal uh, will not be here, it will be immobile. So this is the immobilization, and compartmentalization is another method. So exclusion is the way by which plant can prevent heavy metal to enter into the cytosol. If we want to store this heavy metal inside the vacuole as a defense strategy, that is known as, so vacuole is again a organelles in the plant cell, and if we want to store this heavy metal ion in the vacuole, then this will be known as the compartmentalization. Okay. Yes. So the one important terminology related to phytoremediation is bioconcentration factor. And you have to tell me what do you mean by this bioconcentration factor. So ion concentration in root divided by ion concentration in stem, ion concentration in plant tissue divided by initial ion concentration in solution, ion concentration in solution divided by ion concentration in plant tissue, ion concentration in stem divided by ion concentration in leaves. So Dia gave me B, and Venkateshwara also gave me B. So yes, so this is from that solution how much concentration has been taken up by the living things. Okay, so this will be ion concentration in plant tissue divided by initial ion concentration we had, let's say in the soil or in any solution. So this will be known as the bioconcentration factor. So in phytoremediation, whenever we will have BCF higher, it means more of that metal ion is taken up by the plants. Okay, so this is how it is removing the metal ion from the soil. So that's why BCF should be higher for the plants that have the higher efficiency in phytoremediation. So this is the concentration in organism divided by the concentration in environment. Another factor that is important for the phytoremediation is translocation factor. And this is the ratio of ion concentration in stem or leaves to ion concentration in roots. The ratio of ion concentration in roots to ion concentration in solution, ion concentration in solution to ion concentration in leaves, the total ion concentration in plant tissue per unit biomass. So let me see the answers that you have given me. Priscilla gave me A, and Dia also gave me A. So yes, so this is like from root how much metal is going up into stem or leaves. So this is the translocation. So this you already know that these are the different processes, and so these are some organic compound that we have in the soil, and this organic compound will be taken up by the roots or stems. So this will be the translocation factor. Okay. Which phytoremediation process involves metal accumulation plant that translocate metal from soil to root and concentrate them? So it will take from soil to root, and in that root it will concentrate it. So this will come under what kind of process? As I already have discussed this process: phytovolatilization, degradation, extraction, stimulation, stabilization, and rhizofiltration. Okay, so Dia and Priscilla gave me B, and yes, so this will be the phytoextraction. Rhizofiltration refers to what? Holding contaminated soil in place by vegetation, uptake of contaminant from soil and transferring them, using plant to absorb, concentrate, or precipitate metal contaminant from water, and enhancement of microbial activity in root zone. Priscilla B via C. Let me see which is the right answer. So C is the right answer. So this is plant to absorb, concentrate, and precipitate metal contaminant from water. You can have this table online. So we have phyto extraction. So what is the so this will be the contaminant extraction and capture. Rhizofiltration, contaminant extraction and capture. Then phytostabilization. So we are fixing that contaminant at the root zone and in the roots. In rhizosphere degradation, we are destructing that metal ion in root zone only. Phytodegradation, we are degrading that. We are degrading into some simpler. Volatilization means we are extracting that from the root and we are releasing in the air. So this is how we do have different. Advantage of phytoremediation is it just use the solar energy, and this is making the energy efficient. But the disadvantage of phytoremediation is it can take several years to remediate a site, because we have to grow the plant, then plant will take a lot of year to for the growth and for the extraction of your metal ion. uh, phyto means plant and phyco means algae. So with the help of algae we can remediate wastewater or let's say soil. So this is using the algae. Okay, so phycoremediation is use of algae for reducing or transferring the pollutant. And we do have a lot of type of chamber. In that chamber we can have this algae and the wastewater, and we can remove like organic matter from that wastewater. So we do have different type of chamber, and one closed photobioreactor type in the phycoremediation is vertical tubular. So such kind of things you can see. So just you can see the green color algae and we have vertical column. So likewise, we can remove the contaminants from the water using algae. These are different parameters that we have in the phycoremediation, and this is all. Thank you so much. If you have any problem and query, you can let me know. And thank you so much for too much patience, because it is 2 hour and like listening everything for the 2 hour is too much. So thank you so much for your patience. If you have any problem or query, you can let me know. You can also you can always mail me if you have any query on this. And my mail id is jyoti21 at the rate iiserb.ac.in. And thank you so much guys for too much patience.